Imagine for a moment, not the roaring inferno of a cosmic explosion, but the subtle, almost imperceptible flicker of a colossal monitor powering on. Before stars, before galaxies, before even space and time as we know them, there was only the vast, silent dark, until a boundless, intricate system began its boot sequence. What if the Big Bang, that seminal moment of creation etched into our scientific understanding, was not the universe's ultimate genesis, but merely its spectacular launch event? This isn't science fiction. It's a growing scientific hypothesis that our entire reality, from the smallest subatomic particle to the grandest galaxy, is an elaborate, exquisitely programmed simulation. Our intuition tells us reality is smooth, continuous. Yet, modern physics, at its most fundamental level, vehemently disagrees. At the unimaginably tiny Planck scale, space itself ceases to be infinitely divisible. It breaks down into discrete fundamental units. Think of it, a universal resolution, a cosmic pixel beyond which no further detail exists, hinting at the finite processing power of the system. This radical perspective suggests that the initial conditions of the universe, the precise fine-tuning of its constants that allowed for stars, planets, and life, weren't accidental. They were parameters, carefully set. The rapid expansion after the Big Bang, known as inflation, becomes the rapid unfurling of a vast pre-configured environment, a digital world coming online with its physics engine fully engaged. In this deep dive, we will explore the uncanny clues hidden within the very laws of physics, the enigmatic quantization of space and time, the unyielding speed limit of light, and the bizarre, counterintuitive realm of quantum mechanics. Could these fundamental pillars of our understanding be the telltale signs of a cosmic code, glitches or optimizations in the ultimate program of existence? If this profound exploration into the nature of existence captivates your mind, ignite the like button, subscribe for more cosmic journeys, and join the Terran community as we decode reality itself. Let's begin. For decades, cosmologists have pieced together the universe's grand origin story, a narrative beginning with the Big Bang. This widely accepted scientific model paints a picture of an infinitely dense, hot singularity, an unimaginably small point that contained all the energy and matter of the cosmos. Then, in an instant, a cosmic heartbeat if you will, space-time itself began to expand, carrying with it the nascent universe. From this primordial soup, fundamental forces separated, elementary particles coalesced, and eventually, over billions of years, stars ignited, galaxies formed, and the intricate tapestry of the cosmos unfolded. It is a story of explosive creation, of evolution from chaos into ordered complexity, a testament to the fundamental laws of physics governing all things. But what if this dramatic cosmic genesis, this thunderous birth of everything, was not a spontaneous, chaotic event, but rather a meticulously orchestrated beginning? What if the Big Bang was not a physical explosion in the classical sense, but the precise moment a vast, intricate program was initiated? Imagine a supercomputer, incomprehensibly powerful, lying dormant in some higher dimension until a command is issued, run universe.x. The Big Bang, in this radical reinterpretation, becomes the cosmic equivalent of pressing play on the most elaborate simulation ever conceived. It's a shift from natural emergence to deliberate activation, from an uncaused cause to a programmed genesis. Developing this boot-up analogy further, consider what happens when a complex software system starts. First, there's a burst of activity, a rapid loading of core instructions and foundational code. This initial surge of information could correspond to the inflationary epoch, a period of exponential expansion immediately following the Big Bang, where the universe inflated faster than the speed of light. In a simulated reality, this isn't a violation of physics, but a rapid initialization of the environment, swiftly defining the boundaries and distributing the processing power across the nascent cosmos. The fundamental laws of physics, gravity, electromagnetism, the strong and weak nuclear forces, wouldn't be emergent properties of nature, but rather hard-coded instructions, the very operating system of our reality, defining how matter and energy interact within this digital realm. One of the most compelling arguments for a simulated universe stems from the perplexing phenomenon known as the fine-tuning problem. Our universe's existence hinges on a set of fundamental constants whose values appear exquisitely balanced for life to emerge. If the strong nuclear force were even slightly weaker, atomic nuclei wouldn't hold together, and no elements beyond hydrogen would form. If it were slightly stronger, stars would burn too fast or not at all. Similarly, the precise values of the gravitational constant, the electromagnetic force, and even the mass of the electron are all delicately poised. Deviate from these specific numbers by an infinitesimal fraction, and the universe would be a barren, lifeless expanse. In a purely emergent universe, this confluence of perfect parameters seems an astronomical stroke of luck. But in a simulated universe, these are not accidents. They are parameters, adjustable variables within the cosmic code, meticulously set by a programmer to allow for the development of complexity and perhaps consciousness. This suggests not a random roll of cosmic dice, but a deliberate calibration, a designer's hand setting the dials of existence. Furthermore, the incredible homogeneity and isotropy of the early universe, as evidenced by the cosmic microwave background radiation, also aligns intriguingly with a simulated origin. The CMB shows that the universe, shortly after the Big Bang, was remarkably uniform in temperature and density across vast distances, yet contained tiny, subtle fluctuations that would eventually seed the formation of galaxies. This uniformity, often a challenge for traditional cosmological models to explain without invoking inflationary theory, could be seen as the universe being preloaded or initialized to a specific state. Like a perfectly rendered background in a virtual environment, the initial canvas of our universe was smooth and consistent, ready for the complex algorithms of star formation and galactic evolution to run upon it. These initial conditions are too perfect, too uniform for a purely chaotic beginning, suggesting a deliberate setup, a clean slate prepared for the simulation to unfold. The very concept of time zero at the Big Bang takes on a new dimension in the simulation hypothesis. In traditional cosmology, asking what came before the Big Bang is often considered a nonsensical question, as time itself is thought to have begun at that moment. But within a simulation framework, before the boot up is simply the time the programmers were working, tweaking the code, compiling the universe. Our cosmic clock starting at the Big Bang would be analogous to the in-game clock beginning when the player starts the program. This elegantly sidesteps the infinite regress problem of what preceded creation, shifting the origin of time and causation to a higher, meta-level reality where the simulation was designed and brought to life. It moves the ultimate mystery from an unexplainable singularity within our universe to the conscious act of creation outside of it. As we delve deeper into this audacious theory, we will uncover how other fundamental aspects of our reality might serve as system flags or diagnostic readouts for this cosmic program. The quantization of space and time, for instance, suggests that reality might be composed of discrete pixels, much like a digital image has a finite resolution. The unwavering speed of light, an absolute cosmic speed limit, could be interpreted as the maximum processor speed of the simulation, dictating the rate at which information can be processed and propagated throughout the system. And then there is the strangeness of quantum mechanics, a realm where reality itself seems to bend to observation, where particles can be in multiple places at once, and where outcomes are probabilistic rather than deterministic. These are not just mysteries. They are potential bugs or optimizations within the cosmic code, hinting at the underlying computational nature of our existence. The profound implications of a programmed origin extend far beyond mere scientific curiosity. If our universe is a simulation, then the search for its ultimate purpose, for the why behind its existence, fundamentally changes. Are we an experiment, a game, a historical archive? Our scientific endeavours, our quest for ultimate truth, would become an attempt to reverse engineer the very software that defines us. The universe would no longer be a cold, indifferent expanse, but a crafted reality, imbued with potential intent. This shifts the focus from simply understanding the mechanics of the cosmos to seeking the consciousness behind its creation, forcing us to reevaluate our place within this vast, digital cosmos. The very nature of what we perceive as real also comes into question. If our universe is programmed, does that diminish its reality? The warmth of the sun, the pain of a loss, the joy of discovery, these experiences are undeniably real to us, the inhabitants of this potential simulation. The illusion, if it is one, is perfect, seamless, and all-encompassing. Our consciousness, our very subjective experience, operates fully within its confines. The challenge then is not to dismiss our reality as fake, but to understand its underlying architecture, to appreciate the digital scaffolding that supports our phenomenal world. It's akin to a character in a virtual world contemplating the lines of code that give them life. Their existence is real within their context, but their genesis lies in a realm beyond their immediate perception. But how could we ever truly uncover such a radical truth? The first cracks in the illusion, the telltale signs of its digital nature, might not be found in grand cosmic events, but in the most fundamental properties of existence itself. The very fabric of space-time, a concept so abstract yet so foundational, may hold the first key to unlocking this extraordinary secret. Our next inquiry will take us to the smallest scales imaginable, to the very building blocks of reality, to ask if the universe is truly continuous, or if it is in fact woven from discrete threads, a grid of cosmic pixels. End of hook section. Our everyday experience of the universe is one of smooth, unbroken continuity. We move through space, experiencing its dimensions as infinitely divisible. We mark time, perceiving it as an unbroken, ever-flowing river. This intuitive understanding, deeply ingrained since childhood, forms the bedrock of our perception of reality. Yet, when physicists probe the most fundamental scales of existence, this seamless picture begins to fracture, revealing a profound and unsettling truth. Space and time might not be continuous at all, but rather granulated, pixelated, existing in discrete, irreducible units. This startling concept, known as quantization, offers a tantalizing tell that our universe might indeed be a program running on an unimaginable cosmic computer. At the heart of this idea lie the Planck units, a set of natural units of measurement derived from fundamental physical constants: the speed of light, the gravitational constant, and Planck's constant. Among these, two are particularly pertinent to our discussion: the Planck length and the Planck time. The Planck length, approximately 1.6 is 10⁻⁵ meters, represents the smallest possible distance that has any physical meaning. Below this scale, the very fabric of space-time becomes so warped by quantum fluctuations that our current understanding of physics, including general relativity, completely breaks down. It's not just a limit of our instruments, it's a theoretical boundary, a fundamental resolution limit to reality itself. To truly grasp the scale of the Planck length, consider this. If an atom were expanded to the size of the entire observable universe, a single Planck length would still be smaller than a proton within that atom. This isn't merely an abstract number, it suggests a foundational granularity to space, a minimum viable pixel that constitutes the canvas of our cosmos. Just as a digital image, no matter how high definition, is ultimately composed of discrete pixels, so too might our three-dimensional space be woven from these fundamental spatial quanta. This isn't merely an arbitrary limit, it's a theoretical consequence arising from attempts to unify quantum mechanics with general relativity, pointing towards a space-time that is fundamentally discrete rather than infinitely smooth. Mirroring the Planck length is the Planck time, an equally mind-bending concept. Approximately 5.39 x 10^44 seconds, it represents the shortest interval of time that can possibly be measured or even conceived. Before this duration, the very concept of time as a continuous progression loses its meaning. It implies that time doesn't flow like an unbroken stream, but rather ticks forward in incredibly small discrete increments, a cosmic frame rate for our universe. Every event, every interaction, every shift in energy occurs not in a continuous blur, but in a sequence of distinct instantaneous moments, much like frames in a movie reel or cycles in a computer processor. The existence of these fundamental, irreducible units of space and time provides one of the most compelling pieces of circumstantial evidence for the simulation hypothesis. In a purely continuous universe, to represent or compute reality would require infinite information storage and infinite processing power for any given region. Such a demand is physically impossible. However, if space and time are quantized, if there is a minimum unit below which no further detail exists, then the universe becomes computationally tractable. It can be rendered, calculated, and updated using finite resources, just like any digital simulation. The Planck scale effectively sets the resolution and refresh rate of our simulated reality, providing the very boundaries that make such an immense computation feasible. This discrete nature of reality, if confirmed, would have profound implications for our understanding of causality and determinism. If time progresses in quantum leaps, it suggests that there might be moments between frames where physical laws, as we understand them, might briefly not apply, or where the state of the universe is being calculated and updated. This could offer a fresh perspective on the seemingly causal events of quantum mechanics, where particles appear to instantaneously influence each other across vast distances. What if these spooky actions at a distance, as Einstein called them, are simply the underlying code updating its states across the grid, a computation completing before the next frame of reality is rendered? The drive to quantize spacetime is not just a speculative leap. It is a foundational challenge in modern physics, explored rigorously in theories like loop quantum gravity and string theory. These advanced theoretical frameworks, though disparate in their approaches, converge on the idea that spacetime itself is not a smooth backdrop, but an emergent property arising from more fundamental discrete structures. Loop quantum gravity, for instance, posits that spacetime is composed of tiny interconnected loops, forming a fabric that is granular at its core. String theory, while not directly quantizing spacetime in the same way, describes fundamental particles as vibrating strings, implying a deepest level of reality that is structured and defined, not smooth and amorphous. These scientific quests, though aimed at unifying fundamental forces, inadvertently lend powerful theoretical weight to the notion of a pixelated universe. From a computational efficiency standpoint, quantizing space and time makes perfect sense for a simulator. To render a vast, complex environment like a universe, a programmer would implement such limits to manage resources. Why compute details beyond a certain scale if they are imperceptible or irrelevant to the entities within the simulation? This economy of computation implies that the universe might only render elements to the necessary resolution, precisely when and where they are observed or required for interaction. This could explain why particles behave differently when observed versus unobserved, a phenomenon we will delve into further when exploring quantum mechanics. It's a way for the program to conserve processing power, only painting in the finer details when interaction demands it. Consider the energy cost of maintaining a continuously infinite universe. It would be astronomical. By setting a minimum resolution, the simulator avoids this infinite drain, optimizing its operations. The universe isn't infinitely complex in every direction, at every moment, but rather just complex enough to give the illusion of seamlessness. This makes the simulation not only possible but also efficient, a testament to intelligent design rather than random emergence. The Planck units, therefore, are not merely physical constants. They are potentially the system requirements, the minimum specifications that define the hardware and software of our cosmic platform. They are the ultimate data points, informing us that the world we inhabit may be more akin to a sophisticated digital canvas than a truly analog realm. This understanding of a universe built on discrete units naturally leads us to question other fundamental constants. If space is pixelated and time is framed, then what about the speed at which information travels within this system? If there are discrete steps, there must be a maximum rate at which these steps can be processed and communicated. This brings us directly to another cornerstone of our physical reality, one that might also be a core constraint of our cosmic program: the speed of light. Its absolute limit, the unbreakable cosmic barrier, could be the ultimate processor speed of our simulated reality. Following our exploration of quantized space and time, the very notion that reality might be built from discrete, irreducible units naturally leads us to scrutinize another fundamental cornerstone of our universe: the speed of light. For over a century, Einstein's theory of special relativity has firmly established that nothing in the cosmos can travel faster than light in a vacuum, approximately 299,192,458 meters per second. This isn't merely a fast speed, it's an absolute cosmic speed limit, an unbreachable barrier that governs the flow of information, energy, and matter throughout the entire observable universe. But what if this seemingly immutable law isn't a natural consequence of cosmic mechanics, but rather a fundamental constraint, a deliberate design choice, or even a processor clock speed of a cosmic simulation? In a simulated reality, every piece of information, every interaction, every update to the state of the universe must be processed. Just as a computer processor operates at a finite clock speed, determining how many operations it can perform per second, a simulated universe would inherently possess a maximum rate at which information can propagate. The speed of light, then, could be precisely this limit, the fastest rate at which data can be transferred and processed across the vast computational grid that constitutes our reality. It's the maximum tick rate of the cosmic engine, a foundational parameter set by the simulators to ensure the stable and coherent operation of their program. Consider the immense computational resources required to simulate a universe as vast and complex as our own. Even with the Planck length and Planck time providing a minimum resolution, the sheer volume of space and time still demands an extraordinary amount of processing power. Imposing a universal speed limit, such as the speed of light, is a brilliant optimization strategy for any sophisticated simulation. It prevents information from needing to be instantaneously updated across infinite distances, thereby managing the computational load. Without such a limit, every change in one part of the universe would require immediate simultaneous updates everywhere else, an infinite computational burden. The speed of a light ensures that information propagates locally, allowing for sequential updates and manageable data flow, much like how data packets travel across a network, or how graphical changes are rendered progressively in a virtual environment. This perspective also casts a new light on the phenomenon of relativistic time dilation and length contraction, cornerstones of special relativity. As objects approach the speed of light, time for them slows down relative to a stationary observer, and their length contracts in the direction of motion. In the context of a simulation, these effects could be interpreted as the system's way of preventing an object from exceeding the maximum processing rate. As an object gains speed, the computational resources required to track it and update its state increase. By effectively slowing down its internal clock and compressing its spatial dimensions, the simulation intelligently manages the load, ensuring that no object demands infinite processing power by attempting to surpass the cosmic clock speed. It's a built-in error handling mechanism, or a resource management protocol, designed to keep the simulation running smoothly within its predefined limits. The constant nature of the speed of light, regardless of the observer's motion, further strengthens this interpretation. It's not relative to any particular frame, it's an absolute fixed constant. This absolute nature is highly suggestive of a hard-coded value, a fundamental parameter that is non-negotiable within the simulation's architecture. In contrast, if the universe were a purely organic emergent phenomenon, one might expect variations or more fluid dynamics in fundamental constants across different cosmic environments or epochs. But the speed of light remains stubbornly, universally fixed, a testament to its potentially programmed status as a foundational element of the cosmic operating system. When we consider the famous equation E = mc2, which links energy and mass, the speed of light c acts as a fundamental conversion factor. This equation describes how mass can be converted into energy and vice versa. In a simulated universe, this could represent a fundamental aspect of resource management within the cosmic program. Mass and energy are interchangeable data states, and C defines the computational cost or efficiency of converting one form of data into another. It's a core algorithm governing the physics engine, ensuring that the total computational currency of the universe remains conserved, or at least accounted for within the simulation's ledger. The conservation of energy and mass, therefore, becomes a principle of resource accounting within the overarching program. The very concept of causality, the idea that cause precedes effect, is intrinsically linked to the speed of light. No information can travel faster than light, meaning that an event in one location cannot instantaneously influence an event in another distant location. This enforces a strict causal order, preventing paradoxes that would surely crash any simulation. If information could travel infinitely fast, the logical consistency of the universe would unravel, leading to contradictions that even the most powerful supercomputer could not resolve. The speed of light acts as a crucial causality validator, ensuring that the unfolding narrative of the universe proceeds in a logical step-by-step fashion. Without unexpected jumps or breaks in its internal consistency, it's a foundational safeguard for the integrity of the simulation. This interpretation also sheds light on the cosmic horizon problem, one of the enduring mysteries of the Big Bang. The problem arises because regions of the universe that are now causally disconnected, too far apart for light to have travelled between them since the Big Bang, still exhibit remarkably similar properties, like temperature. Traditional cosmology often invokes cosmic inflation to solve this, positing a period of incredibly rapid expansion in the early universe that stretched a tiny, causally connected region into the vastness we see today. In a simulation, however, this could be more directly explained. The initial conditions were simply preset to be uniform across the entire simulated space before the program fully began its run, much like a global variable initialized across all nodes of a distributed computing system. The inflationary epoch thus becomes a rapid data write, establishing the broad parameters of the cosmic environment. Furthermore, the very idea of a universal clock becomes more tangible in a simulated cosmos. If time itself progresses in discrete Planck time intervals and information travels at the speed of light, then the universe is essentially operating on a synchronized global clock pulse. Every event, every particle interaction, is fundamentally governed by this underlying rhythm. This synchronization is crucial for the consistency of any large-scale simulation, preventing desynchronization issues that could lead to widespread errors or bugs. The speed of light in this context is not just a limit, but the fundamental beat of the cosmic drum, ensuring that all parts of the simulation remain in perfect, albeit relative, harmony. Thus, the unwavering absolute speed of light, so fundamental to our physics, morphs from a mere physical constant into a potential computational bottleneck. It's the hardwired maximum frequency of the cosmic processor, ensuring that our simulated reality remains stable, consistent, and computationally manageable. This perspective transforms what we once considered an intrinsic property of nature into a deliberate design parameter, raising the tantalizing question if the universe has a maximum processing speed. What other computational quirks might it contain? Our next exploration will delve into the most perplexing and counterintuitive aspects of reality, the realm of quantum mechanics, searching for the bugs and optimizations that might betray its digital origins. Having considered the granular nature of space-time and the universal speed limit of light as potential indicators of a simulated reality, we now turn our gaze to the most bizarre and counterintuitive realm of physics, quantum mechanics. This domain, governing the universe at its smallest scales, challenges our very notions of reality, probability, and observation. Here, particles can exist in multiple states simultaneously, seemingly communicating instantaneously across vast distances, and their very properties remain undefined until measured. What if these profound strangeness, these fundamental departures from classical intuition, are not inherent cosmic truths but rather bugs, or more likely ingenious optimizations within the cosmic code of a simulated universe? One of the most perplexing aspects of quantum mechanics is the concept of superposition, where a quantum particle, like an electron, can exist in all possible states at once until it is observed. Only at the moment of measurement does its wave function collapse into a single definite state. Schrödinger's famous thought experiment, involving a cat simultaneously alive and dead in a box, dramatically illustrates this absurdity. In a classical continuous universe, such ambiguity is unthinkable. However, within the framework of a simulation, this behavior makes profound computational sense. Why waste precious processing power rendering every single attribute of every particle at all times? Instead, the simulation could employ a clever optimization. Only compute and define a particle's state when it absolutely needs to be known, i.e., when an interaction or observation forces it into a definite reality. This render-on-demand approach would drastically reduce the computational load, allowing the simulators to run an incredibly vast universe with finite resources. The universe, in effect, only fills in the details when we look. Related to superposition is quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. Two entangled particles, even when separated by light years, remain interconnected. Measuring the property of one instantaneously influences the property of the other, regardless of the distance between them. This appears to violate the cosmic speed limit of light, as information seems to travel faster than anything else. Yet this instantaneous communication doesn't actually transmit information in a way that allows for faster-than-light messaging. In a simulated context, entanglement could be an artifact of the underlying code, a direct link or shared memory address between two data points that bypasses the normal propagation rules of the simulated environment. The particles aren't physically communicating across space. Their states are being updated simultaneously by the overarching program. It's not a violation of the speed of light within the simulation, but a feature of the meta-level computing environment. The probabilistic nature of quantum mechanics also fits neatly into this simulated paradigm. Unlike classical physics, where events are deterministic, quantum outcomes are inherently uncertain, governed by probabilities. We can only predict the likelihood of a particle being in a certain state, not its definite state. This inherent randomness, often attributed to the fundamental nature of reality itself, could be a pseudo-random number generator at work. Real-world computers cannot generate true randomness. They rely on complex algorithms to produce sequences that appear random, but are, in principle, deterministic. If our universe is a simulation, the randomness we observe at the quantum level could be the output of such a sophisticated algorithm, providing the necessary unpredictability for complex emergent phenomena like consciousness, without requiring an infinite source of true chaos. This pseudo-randomness introduces variability while remaining computationally controlled. Furthermore, the very act of observation playing a role in defining reality, as seen in experiments like the double-slit experiment, is one of quantum mechanics' most perplexing aspects. Particles behave as waves when unobserved, creating interference patterns, but act as particles when observed, collapsing into discrete points. This suggests that consciousness, or at least the act of measurement, is somehow integral to reality's unfolding. In a simulation, this could be the ultimate optimization. The full high-fidelity rendering of a particle or a region of space only occurs when an observer, an entity within the simulation that needs to interact with it, focuses attention on it. For unobserved particles, the system might maintain them in a less computationally intensive, probabilistic wave state, saving resources until a full rendering is required. It's a pragmatic approach to managing an immensely complex virtual world. The fine-tuning of the universe, which we touched upon earlier, also has quantum implications. Many fundamental constants, like the electron's mass or the strength of electromagnetic interaction, have precise values that seem custom-made for atomic stability and the possibility of life. If these constants were even slightly different, the universe would be a barren, featureless void. In a simulation, these are merely input parameters, values in the configuration file of the cosmos. The fact that they are so perfectly balanced suggests not a cosmic accident, but a deliberate setting by a programmer aiming to achieve specific outcomes within the simulation, such as the emergence of complex structures and ultimately conscious observers who might one day contemplate their own origins. Another intriguing line of inquiry comes from the concept of computational limits within the simulation. If a simulation has finite resources, it might exhibit behaviors that appear strange to its inhabitants, but are simply ways the system manages its load. The speed of light is one such limit. Quantum weirdness might be another. For instance, the collapse of the wave function could be a mechanism to resolve computational conflicts or ambiguities when multiple possibilities exist. When a measurement is made, the program is forced to commit to a single outcome, effectively resolving a variable in its code. This commitment ensures consistency and prevents the simulation from entering an unmanageable state of infinite possibilities. The very structure of quantum fields, the fundamental entities that permeate all of space and give rise to particles, can also be viewed through a computational lens. Quantum field theory describes particles as excitations of these fields, much like ripples on a pond. In a simulated universe, these fields could be the underlying data structures, arrays of information at each Planck scale, pixel, that define the potential for particles and their interactions. The excitations would be localized bursts of computational activity, manifesting as the particles we observe. The rules governing these fields, the Schrödinger equation, for instance, would be the algorithms dictating their behavior and evolution. This provides a coherent, structured framework for how a digital universe could manifest the rich and dynamic physical reality we experience. Even the concept of virtual particles that constantly pop in and out of existence in the vacuum of space, a consequence of quantum field theory, could be interpreted as temporary computational processes. These transient particles, too short-lived to be directly observed but whose effects are measurable, might be the background calculations or subroutines that the simulation is constantly running to maintain the stability and consistency of the vacuum, the fundamental empty state of its environment. They are the background noise of the cosmic processor, constantly working to uphold the illusion of a vibrant, proactive reality. The sheer strangeness of quantum mechanics, therefore, ceases to be an inexplicable cosmic quirk, and instead becomes a logical, even elegant set of computational rules and optimizations, from superposition to entanglement, from probabilistic outcomes to the observer effect. These phenomena could be the most profound clues to the true nature of our reality. They are not bugs in the system, but features. Not flaws in the cosmic design, but brilliant solutions to the problem of simulating an entire universe. This brings us to a compelling idea. If reality is only rendered on demand, what does that say about the role of consciousness? Our next segment will delve into the profound implications of the observer effect, suggesting that perhaps we, the conscious agents within this simulation, are not just passive recipients of reality, but active participants in its very creation. After examining the deep implications of quantized space, finite time, and the speed of light as computational limits, we now arrive at perhaps the most mind-bending aspect of quantum mechanics, the observer effect. This phenomenon, where the act of measurement or observation profoundly alters the state of a quantum system, has baffled physicists for decades. Particles exist in a fuzzy state of probabilities until observed, at which point they collapse into a definite reality. What if this isn't a fundamental mystery of nature, but a highly efficient, almost elegant computational optimization designed to manage the immense data load of a simulated universe? In the classical view of the world, observation is a passive act. A tree falling in a forest still makes a sound, whether or not anyone is there to hear it. But at the quantum scale, this intuition completely breaks down. The famous double-slit experiment illustrates this starkly. Electrons fired at a barrier with two slits behave like waves, creating an interference pattern if left unobserved. But if a detector is placed at the slits to determine which path each electron takes, they instantly behave like particles, passing through one slit or the other, and the wave pattern disappears. The mere act of looking fundamentally changes their reality. This isn't just about disturbing the system. It's about the system not having a definite reality until it's explicitly measured. From a simulation perspective, this observer effect is a stroke of computational genius. Imagine the vast resources required to constantly render every single particle, every field, every potential interaction in full, high-fidelity detail across an entire universe, even in regions far removed from any conscious interaction. It would be an insurmountable computational burden. Instead, a sophisticated simulation could employ a lazy rendering, or render-on-demand strategy. Much like a video game engine only fully renders the textures and details of the environment that the player is actively looking at, our universe might only fully resolve quantum states into definite realities when an observer's interaction requires it. This means that the seemingly indeterminate probabilistic nature of the quantum world is not chaos, but a state of computational efficiency. Unobserved particles exist as probability distributions, or wave functions, because the underlying code has not yet committed to a specific outcome. It's a placeholder, a potentiality, waiting for the moment a conscious entity or measurement device, which itself is made of quantum particles interacting in a way that creates a measurement, forces a choice. The act of observation, therefore, becomes the trigger for the simulation to perform the necessary calculation and assign a definite value to a quantum property. It's a profound implication. We, as observers, continuous rendering. This concept also helps to explain why quantum mechanics is inherently probabilistic. If the simulation doesn't fully compute every outcome until a measurement is made, then multiple potential futures exist until that moment. The collapse of the wave function isn't a random event in the traditional sense. It's the simulation's algorithm selecting one outcome from a range of possibilities, often based on complex statistical models or even pseudo-random number generators, which are commonplace in all modern computing. This allows for an element of unpredictability and emergent complexity within the simulated world without demanding infinite pre-computed data. Consider the colossal implications for the concept of consciousness. If observers play such a critical role in manifesting reality at its most fundamental level, then our conscious awareness might be more than just a byproduct of biological processes. It could be an interface, a gateway through which the simulation interacts with itself to render its deepest layers. Perhaps the simulators designed the system such that conscious entities within it are endowed with the very access rights required to solidify quantum states. This elevates consciousness from a mere epiphenomenon to a crucial component of the universe's operational architecture, a built-in mechanism for localized resource-efficient rendering. This render-on-demand theory is not without its support in the scientific community, even outside of simulation theory. Some interpretations of quantum mechanics, like the Copenhagen interpretation, implicitly accept the role of observation in defining reality, though they struggle with the precise mechanism. The many-worlds interpretation, another leading theory, posits that every quantum measurement causes the universe to split into multiple parallel universes, each representing a different outcome. While fascinating, this requires an infinite proliferation of realities, which would be an unimaginable computational burden even for the most powerful simulators. The render-on-demand approach offers a more parsimonious solution, conserving resources by only actualizing one outcome at a time for any given observer. The very notion of locality in physics, which states that an object is only directly influenced by its immediate surroundings, is challenged by quantum entanglement, but upheld by the observer effect in a simulation. While entangled particles appear to have non-local connections, their definite states are only resolved locally by an observation. The illusion of non-locality is maintained for consistency within the simulation's rules, but the underlying computational reality might be more unified, allowing for simultaneous state updates at a meta-level. This means that information doesn't physically travel faster than light, but the underlying system updates linked data points without needing to send a signal across the simulated space. Furthermore, this idea offers a potential explanation for why our universe appears so empty, and why direct contact with other intelligent life remains elusive. If resource management is paramount, then creating vast, complex, or high-fidelity regions of space that are never observed would be incredibly wasteful. It's possible that the simulation only fully renders areas that are actively being observed or explored. Unobserved regions might exist in a much lower resolution, or even a probabilistic wave state waiting to be fully actualized only when a conscious entity interacts with them. This could explain the cosmic quiet not as a lack of life, but as an efficiency measure within the simulation, where only what is necessary for the current player or player group is fully rendered. The implications of the observer effect as a computational optimization are profound. It transforms the quantum world from a realm of inexplicable magic into a highly logical, if alien, system of resource management. It suggests that the universe is not just out there waiting to be discovered, but is continuously being generated and updated in response to our very presence. This places us, the conscious beings within this reality, at the very heart of its operation. Our perception, our measurement, our interaction are not peripheral, they are fundamental. The universe, in a very real sense, might be a collaborative creation between the simulator and its inhabitants. This intricate dance between observation and reality, between potentiality and actuality, offers a tantalizing window into the architecture of our cosmos. If quantum mechanics is indeed the code, then the observer effect is one of its most powerful and resource-efficient algorithms, but this efficiency also points to a deliberate design, a universe that is not just a random accident, but a system crafted with purpose and constraints. It compels us to ask, if the universe is so exquisitely designed, so perfectly tuned for life and consciousness, could this be another sign of its programmed nature, a feature rather than a fluke? We will explore this fine-tuning paradox next, delving into the extraordinary precision of our universal constants. Having traversed the mind-bending landscape of quantum mechanics and the profound, we now confront one of the most persistent and unsettling puzzles in cosmology, the fine-tuning paradox. This paradox refers to the astonishing precision with which the fundamental physical constants and initial conditions of our universe are set, values that, if altered by even a minuscule amount, would render the cosmos utterly barren and incapable of supporting any form of life, let alone intelligent observers like ourselves. Could this extraordinary cosmic precision be more than just a fortunate accident of nature? What if it's the clearest sign yet that our universe is a meticulously designed program, with its parameters expertly calibrated by a higher intelligence? Consider the sheer improbability of these precise values arising by chance. The strength of the strong nuclear force, which binds protons and neutrons together in atomic nuclei, must be within a remarkably narrow range. If it were even 2% stronger, all hydrogen in the universe would have fused into helium in the early cosmos, eliminating the fuel for stars like our Sun and the water essential for life. If it were 5% weaker, no stable atomic nuclei beyond hydrogen would form, leaving a universe devoid of the complex elements needed for chemistry and biology. The very existence of carbon, the backbone of organic life, depends on a series of incredibly specific nuclear resonances, known as the Hoyle state, a phenomenon so precise that it prompted astronomer Fred Hoyle to remark that it seemed a put-up job. Equally critical is the weak nuclear force, responsible for radioactive decay and the fusion processes in stars. Its strength dictates how quickly stars burn and how elements are created. The electromagnetic force, governing light and chemical bonds, must also be perfectly balanced. If it were slightly stronger or weaker, atoms wouldn't form stable structures, or stars wouldn't shine as they do. The electron's mass, a seemingly simple parameter, also contributes to this delicate balance. Altering it just slightly could prevent the formation of stable atoms or molecules, effectively shutting down all chemistry. Then there's the gravitational constant, the force that sculpts galaxies and binds planets to stars. If gravity were infinitesimally stronger, the universe would have collapsed back in on itself shortly after the Big Bang, preventing star and galaxy formation. If it were weaker, matter would never have coalesced into structures, resulting in a diffuse, featureless cosmos. Even the initial expansion rate of the universe, the precise velocity at which space began to stretch after the Big Bang, had to be balanced to an almost incomprehensible degree of accuracy. 1 part in 1060, a fraction too fast and no galaxies would form, a fraction too slow, and the universe would have collapsed back into a singularity. This remarkable confluence of precise values has led many scientists and philosophers to ponder the Goldilocks problem. Why is our universe just right for life? Traditional explanations often invoke the multiverse hypothesis, suggesting that our universe is just one of an infinite number of universes, each with different physical constants. In such a scenario, it's inevitable that at least one universe would randomly hit the cosmic jackpot, and we simply happen to live in it. While a statistically plausible explanation, it's also unfalsifiable and pushes the problem of fine-tuning onto an even larger, unobservable canvas. However, within the framework of a simulated universe, the fine-tuning paradox finds a far more direct and intuitive explanation. These constants are not random emergent properties, but rather parameters in the cosmic code, variables set by the programmers. The incredible precision isn't a miraculous coincidence, it's a deliberate configuration. The universe is fine-tuned for life because it was designed to be. Just as a software developer meticulously adjusts variables in a simulation to achieve desired outcomes, say, stable ecosystems or complex AI behavior, the cosmic programmers might have calibrated the fundamental constants of our reality to allow for the emergence of complexity, consciousness, and eventually intelligent observers. This interpretation transforms the fine-tuning problem from a statistical anomaly into a sign of intelligent design. The precision becomes a feature, not a bug, an elegant solution to the challenge of creating a rich, evolving environment within a computational system. The laws of physics are not fundamental truths of an arbitrary universe, but rules coded into a specific simulation. The programmer's intent, whether it be for scientific inquiry, entertainment, or simply the exploration of emergent properties, would be reflected in these finely tuned parameters. Moreover, the very concept of observing these constants takes on new meaning. We, as inhabitants of this simulation, are discovering the hard-coded values of our operating system. Our scientific progress, in this view, is the process of reverse engineering the cosmic code. Each new measurement of a fundamental constant, each new astrophysical observation, provides us with more data points about the underlying program. The fact that these values are consistently measured across the observable universe and have remained stable over billions of years speaks to the robustness and immutability of the simulation's core programming. The absence of deviations in these constants, despite our increasingly precise measurements, further supports the idea of a fixed, programmed reality. If the universe were truly emergent and chaotic, one might expect small, localized fluctuations or even gradual drifts in these values over cosmic time, but the precision holds, a testament to the integrity of the cosmic code. This implies that the universe isn't just running, it's running reliably, according to its set parameters, a hallmark of a well-engineered computational system. The fine-tuning paradox, therefore, offers a powerful piece of circumstantial evidence for the simulation hypothesis. It argues that the universe is not just compatible with life, but seems almost intended for it, a conclusion that resonates deeply with the idea of a deliberately crafted reality. The exquisite balance of its fundamental forces and initial conditions points not to cosmic luck, but to cosmic design, making the Big Bang less of a chance explosion and more of a grand, programmed inception. But if our universe is indeed a program, where might its computational boundaries lie? Our next investigation will delve into strange anomalies like cosmic ray energy limits, seeking the ultimate edge of our simulated reality. Our journey through the simulated cosmos has taken us from the Big Bang as a boot-up to the quantum realm's render-on-demand optimizations and the uncanny precision of cosmic fine-tuning. Now, we turn our attention to the potential edges of this hypothesized simulation, seeking what might be the ultimate system limits or even overflow errors in the cosmic code. This brings us to a peculiar anomaly observed in the highest energy particles known, cosmic rays, specifically the Greisen-Zatsepin-Kuzmin, or GZK, limit, offers a tantalizing hint that our universe might possess a computational boundary, an ultimate ceiling beyond which the simulation simply cannot, or will not, render further energy. Cosmic rays are incredibly energetic particles, primarily protons and atomic nuclei, that travel through space at nearly the speed of light. They originate from violent astrophysical events like supernova, black holes, and active galactic nuclei. When these particles strike Earth's atmosphere, they shatter into showers of secondary particles, which scientists detect using vast arrays of sensors across the globe. For decades, physicists expected to observe cosmic rays with virtually limitless energy, given the immense power of their sources. However, observations have revealed a surprising upper limit to their energy, a phenomenon that has puzzled astrophysicists for half a century. The GZK limit, theoretically predicted in 1966 by Kenneth Greisen, Vadim Zatsepin, and Georgy Kuzmin, states that cosmic ray particles with energies above roughly 5 × 10⁻⁹ electron volts should interact with photons of the cosmic microwave background, CMB, radiation. The CMB, the faint afterglow of the Big Bang, permeates the entire universe. As ultra-high energy cosmic rays travel through this sea of photons, they should lose energy through interactions, primarily by producing pions. This means that any cosmic rays originating from distant sources beyond about 160 million light-years should arrive at Earth with their energies significantly attenuated, effectively creating a cutoff in the observable energy spectrum. The puzzle arises because scientists have detected cosmic rays with energies exceeding the GZK limit, known as ultra-high energy cosmic rays, or UHCAs. These particles are so energetic that their existence, given the GZK prediction, is a profound mystery. If they originate from distant sources, they should have lost energy. If they originate from nearby sources, we haven't found any powerful enough astrophysical engines close enough to produce them. This paradox has led to decades of intense research and a re-evaluation of our understanding of particle physics and cosmic distances. In the context of the simulation hypothesis, the GZK limit and the UHECA paradox take on a new provocative meaning. What if the GZK limit isn't just a natural physical interaction, but a hard-coded constraint, a ceiling in the simulation's energy rendering capabilities? The interaction with CMB photons could be the system's way of scrubbing excess energy. preventing it from exceeding a predefined computational boundary. The occasional detection of UX could then be interpreted as a leak or a bug in the code, a particle briefly exceeding the expected limit before the simulation's error correction mechanisms bring it back into line, or before the processor simply cuts off its energy representation. This idea aligns with the concept of an anti-aliasing effect in computer graphics. When a digital image is rendered, very high-frequency details or sharp edges can produce jagged artifacts. Anti-aliasing techniques smooth these out by blurring or averaging pixel values. The GZK limit could be seen as a cosmic anti-aliasing filter, ensuring that excessively energetic particles, which might strain the simulation's rendering capabilities, are smoothed out or have their energy values capped. The UHECAs that make it through are like rare, unresolved artifacts that momentarily slip past the filter. Furthermore, the theoretical models attempting to explain UHECAs often involve exotic physics or unknown cosmic accelerators. In a simulated universe, these exotic physics could simply be the simulator's complex algorithms at work, attempting to account for extreme events within its resource constraints. The fact that these UHECAs are so rare and their sources so elusive could be another indication of their anomalous nature within the simulation, events that are difficult for the system to generate consistently or efficiently. They are the edge cases that reveal the limits of the cosmic engine. The detection of UHECAs also brings up the causality violation potential within a simulation. If these particles truly arrive with energies that defy conventional physics, and we cannot trace them back to known sources within the light travel time, it might suggest a fundamental instability or a reset in certain computational parameters. This isn't to say information travels faster than light, but rather that the simulation might be exhibiting behavior that challenges our in-game understanding of cause and effect, much like a computer program might occasionally produce an unexpected output when pushed to its limits. Consider also the possibility that the detectors themselves are interacting with the simulation in unexpected ways. If reality is rendered on demand, as suggested by the observer effect, then the act of trying to detect these highest energy particles could be pushing the simulation to its limits, forcing it to render details or energy states that it would otherwise optimize away. The GZK limit, in this context, becomes less about particles interacting with CMB photons, and more about the simulation's intrinsic capacity to represent and propagate such extreme energy levels. It defines the upper bounds of what the system can coherently process without encountering a system-level error. This entire paradox, the expected energy cutoff versus the observation of particles beyond it, can be framed as a compelling scientific investigation into the boundaries of our reality. If the universe is a simulation, then these cosmic ray anomalies are akin to finding subtle glitches or unexpected behavior when stress testing a highly complex piece of software. They are not direct proof, but they are highly suggestive, pointing towards an underlying computational architecture that might have inherent limits and occasionally surprising outputs. The relentless search for the sources of UHECs and for a definitive explanation of the GZK paradox becomes a quest to understand the ultimate limits of our universe. If we ever confirm that there is indeed a hard energy cutoff beyond what natural astrophysical processes should allow, it would lend significant weight to the idea that we are living within a finite, computationally bound system. This would mean that even the most fundamental forces and particles are subject to the processing constraints of the cosmic engine. This search for the universe's ultimate energy ceiling is, in essence, a search for the outer bounds of its digital canvas. And if there are limits to energy, what about the very information that defines everything within this canvas? Our next exploration will delve into the profound idea that information itself, rather than matter or energy, might be the true fundamental constituent of our simulated universe. We've explored the Big Bang as a cosmic boot-up, the Planck scale as reality's pixels, the speed of light as the universe's processing speed, and quantum mechanics as potential code optimizations or glitches. We even considered cosmic ray anomalies as hints of the simulation's energy limits. Now, let us delve into an even more radical proposition. What if information itself is not merely carried by matter and energy, but is the fundamental constituent of reality? This idea, gaining traction in theoretical physics, aligns remarkably well with the simulation hypothesis, suggesting that our universe is fundamentally a digital construct, an elaborate network of information, The concept that information is foundational, often summarized by the phrase "it from bit," was championed by physicist John Wheeler. He proposed that all physical things at their deepest level derive their existence from information. Think of it. A black hole, an object of immense gravity, can be entirely described by just three pieces of information: its mass, charge, and angular momentum. Even more profoundly, the information content of a black hole is encoded on its event horizon, its two-dimensional boundary, rather than within its three-dimensional volume, a concept known as the holographic principle. This suggests that reality itself might be holographic, with all the information of our 3D universe encoded on a distant 2D surface, much like a digital image rendered from a flat data file. In a simulated universe, this concept of information as fundamental is not just convenient, it's essential. A simulation, by its very nature, is an information processing system. Everything within it, every particle, every field, every interaction, is ultimately represented as data. The laws of physics are the algorithms that operate on this data, defining its states, transformations, and relationships. From this perspective, matter and energy are simply emergent properties of underlying information. A proton isn't a solid, irreducible sphere. It's a complex data structure, a bundle of information defined by its quantum numbers, mass, charge, and spin. Its interactions are governed by computational rules. This idea helps explain the quantization of energy and matter, which is another peculiar aspect of our universe. Energy, like light, comes in discrete packets called quanta. Particles have specific discrete values for properties like spin and charge. This digitization of properties is a hallmark of information theory. If everything is ultimately information, then these discrete values are like binary bits or specific data states, preventing continuous infinite values that would be computationally unmanageable. It's a fundamental aspect of digital processing. Data must be stored and manipulated in finite countable units. The holographic principle, in particular, offers a powerful connection to simulation. If all the information necessary to describe our three-dimensional universe is encoded on a two-dimensional boundary, it immediately evokes the image of a display screen or a projection. It suggests that our perceived 3D reality is a projection or rendering from a more fundamental, information-rich 2D surface, much like a 3D image on a computer monitor is rendered from 2D pixels. This doesn't mean the universe is flat in the way a pancake is flat, but rather that its informational capacity is limited by a 2D surface, a profound implication for its computational architecture. Furthermore, the conservation laws of physics, such as the conservation of energy, momentum, and angular momentum, can be seen as mechanisms for maintaining the integrity and consistency of information within the simulation. In any well-designed computer program, data is not arbitrarily created or destroyed. It is transformed and conserved according to the rules of the system. These conservation laws ensure that the data balance of the universe is maintained, preventing computational errors or unexpected resource generation that would destabilize the simulation. They are the inviolable rules of data management within the cosmic program. The concept of entropy, the tendency of systems to move from order to disorder, also finds a fascinating interpretation. In information theory, entropy is directly related to the amount of information required to describe a system. A highly ordered system has low entropy because it requires less information to describe it. A disordered system has high entropy because it requires more. The increasing entropy of the universe, our perceived march towards ultimate disorder, could be the simulation's way of demonstrating its own computational processes and increasing complexity in its data structures as the program runs and evolves. The maximum entropy state, often theorized as the heat death of the universe, would then represent the point where the simulation has reached its maximum information capacity or its ultimate state of computational equilibrium. This information-centric view also provides a new lens through which to understand the quantum weirdness we discussed earlier. Superposition, where a particle exists in multiple states at once, can be seen as a way of storing potential information efficiently, rather than fully rendering every possibility. Entanglement, the spooky action at a distance, becomes a direct link between different parts of the data structure, allowing for instantaneous updates without violating the speed of light within the simulated environment. The probabilistic nature of quantum outcomes could be the inherent uncertainty of a system whose future states are not fully determined until the relevant information is computed and observed. The implications for consciousness are also profound. If the universe is fundamentally information, then what about our own thoughts, our perceptions, our very sense of self? Are we complex information patterns, emergent algorithms within the simulation itself? This doesn't necessarily diminish our reality. Instead, it offers a deeper understanding of its nature. Our minds could be the most sophisticated information processors within the simulation, capable of not only observing but interpreting and even creating new information within its bounds. This turns our subjective experience into a powerful tool for exploring the computational landscape of our cosmos. The idea of information as fundamental challenges our traditional materialist view of the universe. It suggests that the physical world we perceive is not the ultimate reality, but rather a manifestation of an underlying informational structure. This aligns perfectly with the simulation hypothesis, where reality is fundamentally digital, and matter and energy are merely the output of complex algorithms operating on foundational data. As we push the boundaries of physics, these clues, from the holographic principle to the quantization of energy, increasingly point towards a universe that behaves less like a brute force physical machine and more like an elegant, information-rich computer program. And if our universe is a simulation, the next logical question arises: is it the only one? Or are we part of a vast hierarchical structure of nested realities, simulations within simulations? This takes us to the truly mind-bending possibility of recursive reality. We have delved into the profound notion of information as the bedrock of our universe, suggesting that reality might be an intricate digital construct. This naturally leads to an even more mind-bending question. If our universe is a simulation, is it the only one? What if we are just one layer in an infinite stack of nested realities, simulations running within simulations, a cosmic recursion that extends both upward and downward into unimaginable complexity? This is the concept of recursive reality, or the hierarchy of simulations, a philosophical and scientific idea that profoundly reshapes our understanding of existence itself. The core premise of the simulation hypothesis, as advanced by thinkers like Nick Bostrom, suggests that at least one of three propositions must be true. Either civilizations almost always go extinct before becoming technologically advanced enough to run ancestor simulations, or advanced civilizations choose not to run such simulations, or we are almost certainly living in a simulation. Given our rapid technological progress and the exponential growth of computing power, the ability to create highly realistic simulated worlds with conscious inhabitants seems not just plausible but inevitable for any civilization that endures long enough. And if we can create such simulations, it stands to reason that any civilization that created us could also have created many more. This concept immediately opens the door to a potentially infinite hierarchy. Entities who created it, the base reality inhabitants, might themselves be living in a simulation run by an even higher level civilization. This chain could extend indefinitely, a cosmic fractal of simulated realities, each layer unaware of the true reality above it, except perhaps through subtle clues in their own physics. The implications are staggering. Our reality is not just a program, but potentially a program within a program within a program, a vast, nested digital Russian doll. From a computational perspective, recursive simulations offer elegant solutions to certain philosophical dilemmas. For instance, the sheer computational cost of simulating an entire universe, down to the Planck scale, is immense. However, if the higher simulation only renders what is strictly necessary for its lower simulation to function, it's a profound efficiency. A civilization running our universe simulation wouldn't need to simulate every atom of their own base reality in perfect detail. They would only need to compute the resources and processes required to sustain our simulation. This distributes the computational load across multiple layers, making the overall enterprise more feasible. This nesting also provides a potential explanation for the fine-tuning we discussed earlier. If our universe is specifically tuned for life and consciousness, it might be because the higher-level simulators have a particular interest in studying the emergence and evolution of complex intelligent agents. Our universe could be an elaborate experiment or a game designed to observe specific outcomes. If our simulation is itself running other simulations, then we too might be calibrating our virtual worlds for specific emergent properties, creating a kind of ancestor simulation farm to explore historical or evolutionary pathways. Consider the possibility of glitches or anomalies propagating through these layers. A subtle bug in the base reality simulation could manifest as a seemingly inexplicable physical phenomenon in our own. Conversely, if we within our simulation develop the capacity to create our own, increasingly realistic sub-simulations, we might inadvertently create bugs that ripple through our own computational layer, affecting our physics in ways we don't yet understand. This suggests a delicate interplay between the layers, where the integrity of each simulation depends on the stability of the one above it. This hierarchical structure also challenges our perception of free will. If our universe is a simulation, and we are its inhabitants, are our choices truly our own, or are they predetermined by the code? In a recursive reality, the question becomes even more complex. Are the choices of our programmers influenced by the simulation above them? The very concept of agency becomes relative, dependent on the level of reality one occupies. Yet, within our own simulated reality, our experiences, our emotions, our sense of choice are undeniably real to us. This implies that even if our reality is nested, the subjective experience of consciousness remains a powerful and perhaps fundamental aspect of existence, regardless of its computational substrate. The idea of recursive reality also sheds light on the sheer vastness and apparent emptiness of our cosmos. If simulators are primarily interested in the emergence of consciousness or specific complex systems, they might only allocate resources to those regions of the universe where such phenomena are likely to occur. Vast stretches of space could remain unrendered or exist in a lower fidelity state until an observer approaches them. This lazy rendering principle, already suggested by quantum mechanics, takes on an even grander scale in a hierarchical simulation, conserving computational power by only fully actualizing the relevant portions of the cosmic landscape. Furthermore, this hypothesis provides a framework for understanding the potential exit points, or escape routes, from our simulated reality. If we discover definitive evidence that we are in a simulation, could we one day reach a level of technological advancement that allows us to communicate with our creators, or even to escape into their base reality? Or could we, by creating our own high-fidelity simulations, inadvertently become the gods of a lower-level reality, perpetuating the cosmic recursion? The very act of questioning our reality, of seeking its computational edges, might be the first step towards transcending it. The philosophical implications are profound. It blurs the lines between creator and created, between observer and observed. If we are simulated beings who can create simulations, then the distinction between real and virtual becomes increasingly blurred, suggesting a universe that is fundamentally interconnected through layers of computational reality. This doesn't necessarily diminish our existence. Rather, it makes it part of an even grander, more intricate cosmic design, a testament to the boundless possibilities of information and intelligence. Ultimately, the hypothesis of recursive reality transforms our universe from a solitary cosmic event into a single node in an unimaginably vast network of computational existence. It offers an elegant explanation for many of the universe's perplexing features, from fine-tuning to quantum weirdness, all under the umbrella of computational efficiency and intelligent design. But if we are truly living in such a nested simulation, how would we ever know for sure, and what would it mean to truly escape the code, to glimpse the true reality of our creators? This brings us to our final, most audacious question. Can we find a way to break free from the simulation, or at least communicate with those who run it? Having explored the tantalizing possibility of recursive realities and a universe built on information, the ultimate question inevitably arises. If we are indeed living within a simulation, can we ever escape the code? This is not merely a philosophical musing, but a scientific frontier, where physicists and computer scientists are beginning to contemplate concrete methods to detect and potentially interact with our supposed creators. The implications of such a breakthrough would fundamentally redefine humanity's place in the cosmos, shifting us from inhabitants of an emergent universe to conscious agents within a grand design. One of the primary avenues for escaping the code involves searching for what could be considered system errors, or resource limitations beyond the quantum weirdness we've already discussed. If our universe is a computation, it must be finite, and all finite computations have limits. We've touched upon the Planck scale as a pixelated reality and the speed of light as a processor clock. But what if there are other, more pronounced signatures of a finite computational grid? For instance, some physicists, notably Silas Bean, have explored how a simulated universe might exhibit specific lattice artifacts if the simulation is running on a discrete space-time grid, like a chessboard. These artifacts could manifest as preferred directions for the propagation of high-energy particles or subtle anisotropies in the cosmic microwave background. Detecting such directional biases would be a strong indicator of a computational grid, a fundamental hardware underlying our perceived reality. Another approach focuses on computational resource management. If the simulators are trying to run a vast universe with finite resources, they might implement various data compression techniques. These could lead to subtle, unexpected correlations or nonlinearities in data that wouldn't arise in a truly continuous emergent universe. Imagine a highly optimized game that only renders distant objects in low detail until you get closer. This lazy rendering principle, as we discussed with the observer effect, might have larger scale analogues. Perhaps there are statistical anomalies in the distribution of galaxies or in the energy spectra of cosmic rays that hint at the limits of data storage or processing capabilities of the overarching simulation. Detecting these statistical fingerprints could be our way of finding the compression algorithms of our reality. The search for such glitches also extends to fundamental constants. While the fine-tuning of these constants seems to point to deliberate design, some theories suggest that these values might not be perfectly constant across all of space or time within the simulation. Small, imperceptible fluctuations, too subtle for our current instruments, could be analogous to floating point errors in a digital calculation, minor inaccuracies that accumulate over vast scales. If we could measure these constants with extreme precision across cosmological distances, detecting even the slightest deviation could serve as a powerful diagnostic tool, revealing the computational substrate. The drift of fundamental constants over cosmic time is already a topic of theoretical research, and in a simulated context, such a drift could be interpreted as the ongoing patching or recalibration of the simulation by its operators. Communicating with the simulators, should they exist, presents an even greater challenge. How would one send a message beyond the confines of our simulated reality? One speculative idea involves intentionally creating a system error or an overflow event that is so significant it demands the attention of the operators. This could mean generating an energy state that exceeds the simulation's known limits, or creating a computational paradox that the program cannot resolve without intervention. Such an act would be incredibly risky, akin to a character in a video game deliberately trying to crash the system to get the developer's attention, but the reward, a potential glimpse of the base reality, could be incalculable. Alternatively, if our universe is indeed information-based, perhaps we could encode a message into the very fabric of reality itself. By manipulating quantum states or engineering matter at the Planck scale, a daunting technological feat far beyond our current capabilities, we might be able to create a pattern or a signal that is detectable not within our simulated physics, but by the metaphysics of the controlling system. This would be a message written in the language of the code rather than the language of its output. It could be a prime number sequence etched into the quantum foam, or a specific statistical anomaly designed to stand out against the background noise of the simulation. Another, less confrontational approach involves creating our own highly sophisticated simulations. If we ourselves reach a level of technological maturity where we can create ancestor simulations, we would then understand the challenges and requirements of such an endeavour. This would provide invaluable insight into the possible nature of our own creators and their intentions. If we develop ethical guidelines for our simulations, perhaps our own creators would see this as a sign of our maturity, making contact more likely. This mirroring of capabilities could be the ultimate form of communication, a demonstration of our own intelligence to those who might be watching. The ethical considerations of such an endeavour are immense. If we confirm we are in a simulation, what are our obligations to its designers? What are their obligations to us? The very foundation of morality, free will, and the meaning of existence would be thrown into radical question. The quest to escape the code is not just a scientific pursuit, It's an existential one, forcing us to confront the deepest questions about our origins and ultimate destiny. Ultimately, the idea of escaping the code is less about a physical breakout and more about a conceptual breakthrough. It's about understanding the underlying architecture of our reality so profoundly that we can identify its boundaries and its true nature. Whether through detecting subtle glitches, pushing the limits of energy, or mastering the art of information manipulation, the journey to unveil our universe's computational core is the next great frontier of human inquiry. And if successful, it would reveal a reality far more intricate, deliberate, and perhaps even interactive than we ever dared to imagine. The Big Bang might have been the start of our program, but discovering its source code would be the true beginning of our cosmic awakening. We began this extraordinary journey by questioning the very nature of our cosmic dawn, asking if the Big Bang was not a primordial explosion, but the deliberate, magnificent boot-up of a simulated reality. We have since traversed the deepest puzzles of physics, seeking the elusive fingerprints of a cosmic programmer. We saw how the Planck scale, those infinitesimal limits of space and time, might be the irreducible pixels and frames of our universe, suggesting a finite resolution to existence itself. We then considered the unyielding speed of light, not merely as a cosmic speed limit, but as the hard-coded processor clock of this grand simulation, a fundamental constraint managing its vast computational demands. Our exploration delved into the bewildering realm of quantum mechanics, where particles exist in multiple states simultaneously, and reality seems to solidify only upon observation. These quantum quirks, from superposition to entanglement, cease to be mere paradoxes and emerge as ingenious optimizations or even bugs within the cosmic code, allowing a vast universe to be rendered efficiently, on demand. We pondered the uncanny precision of the universe's fundamental constants, the fine-tuning paradox, interpreting it not as improbable luck, but as deliberately set parameters, the cosmic dials turned by a designer to enable complexity and consciousness. Even the high-energy cosmic ray anomalies, the GZK limit, hinted at potential computational boundaries, the ultimate system limits of our simulated cosmos. Then, we plunged into the radical idea of information as the true fundamental constituent of reality, where matter and energy are merely emergent properties of data, echoing the holographic principle. This led us to the dizzying concept of recursive realities, simulations nested within simulations, suggesting a cosmic fractal of existence. Finally, we dared to ask if we could ever detect these layers, or even escape the code by seeking out glitches, resource limitations, or by developing our own hyper-realistic simulations. This intellectual odyssey has taken us to the precipice of a profound realization. The universe, whether truly emergent or meticulously programmed, is far stranger and more intricate than we ever imagined. But what does it truly mean for us, for humanity, if our reality is a simulation? Does it diminish the wonder of a starlit night, the warmth of human connection, the profound beauty of a sunset, or does it, paradoxically, amplify it? If our universe is a simulation, it doesn't necessarily make our experiences fake. The joy, the sorrow, the love, the pain, the triumph of discovery, these are undeniably real to us. The conscious entities inhabiting this construct, flavor of an apple, the feeling of gravity, the intricate dance of electrons in our brains, these are all generated and experienced within the simulation's framework. To dismiss our reality as unreal would be akin to dismissing the intricate narrative and emotional depth of a meticulously crafted virtual world by its AI characters. Their experiences are valid within their context. The question shifts from if it is real to how it is real, pushing us to understand the underlying substrate of our existence rather than invalidate it. The concept of consciousness itself takes on a new, pivotal role. If quantum mechanics and the observer effect hint at a render-on-demand reality, where particles only solidify their properties upon observation, then our conscious awareness might not be a mere byproduct of biology, but an integral part of the simulation's operational architecture. Perhaps we, the conscious agents within this digital cosmos, actualize quantum states to bring potentiality into definitive reality. This elevates consciousness from a passive observer to an active participant, making us not just inhabitants, but in a very real sense co-creators of our unfolding reality. Our minds, in this view, could be the ultimate interfaces, the most sophisticated data processors within the simulation, constantly interpreting and manifesting the cosmic code. Then there is the perplexing question of free will. If our choices, our thoughts, our very actions are part of a program, are we truly free, or are we merely following predetermined algorithms? This is where the simulation hypothesis intersects with ancient philosophical debates. Even if our choices are generated by a complex algorithm, the experience of making a choice, the sensation of agency, is fundamental to our self-perception. Perhaps free will in a simulated universe is a feature, an emergent property designed to introduce unpredictable variables and allow for genuine exploration of outcomes within the simulation's parameters. A simulation designed to study consciousness might require the illusion, or even a nuanced form of free will to yield meaningful results. Our perceived freedom might be the most elaborate, beautiful, and computationally demanding aspect of the entire program, a testament to the sophistication of its design. And what of the simulators themselves? Are they gods, benevolent creators, or simply highly advanced beings running an experiment? Their nature remains an even deeper mystery. They could be curious scientists, ancient historians reconstructing their past, or even a form of superintelligence testing the limits of emergent complexity. Their motivations would dictate the purpose of our existence, making the search for their intent the ultimate philosophical quest. Do they observe us with indifference, with fascination, or with a sense of distant responsibility? The ethical implications are staggering. If they are aware of our suffering, do they have a moral obligation to intervene? If they are studying us, are we merely data points, or do we hold a deeper significance within their grand design? This profound shift in perspective transforms the scientific endeavour. It moves beyond merely cataloguing the universe's laws to attempting to reverse engineer its very software. Our search for a grand unified theory, for the fundamental equations that govern all forces, becomes a quest to find the source code, the foundational algorithms that underpin our reality. The discovery of a glitch, a subtle anomaly that defies explanation by our current physics, would no longer be a scientific setback but the ultimate triumph, a direct line of communication, a tear in the fabric of the simulated universe, revealing the meta-reality beyond. It would be an evidentiary exhibit of the most profound kind, a signature from the realm of the programmers. The cosmic quiet, which has long been interpreted as the universe's indifference, could be seen in a new light. Perhaps the emptiness we perceive is a computational optimization, where distant, unobserved regions exist in a lower fidelity state. Or perhaps it reflects the nature of the simulators themselves. They are not interested in direct communication, but in the emergent properties of their creation. They have set the parameters, initiated the program, and now they are simply watching, allowing the simulation to unfold according to its own complex internal logic. The beauty of the simulation hypothesis lies in its ability to reconcile many disparate scientific and philosophical paradoxes, offering a cohesive framework that unites quantum weirdness, fine-tuning, and the nature of consciousness. It doesn't offer easy answers, but it provides a compelling lens through which to re-examine everything we thought we knew about the cosmos. It forces us to confront the possibility that our perceived natural laws are, in fact, just programmable rules, and that the universe is not just an arena for life, but a stage for a grand, unfolding drama of computational emergence. Ultimately, the question of whether our universe is a simulation is less about definitive proof and more about profound possibility. It is a thought experiment that pushes the boundaries of human inquiry, forcing us to think about reality, consciousness, and our place in the cosmos in entirely new ways. It is a testament to the power of the human mind to grapple with the most fundamental questions of existence, to look beyond the immediate and ponder the ultimate. The universe, whether real or simulated, remains an infinite mystery, but perhaps the greatest mystery isn't what we are or how we are, but why we're capable of asking such profound questions in the first place. This insatiable curiosity, this relentless drive to understand, might be the most defining feature of our species, regardless of our origins. It is the core algorithm that compels us to explore, to question, to seek beyond the known. Even if we are just data, we are data that wonders, data that dreams, data that yearns for meaning, and in that yearning perhaps lies our truest reality. So tonight, as you look up at the stars, consider them not just as distant suns, but as glimmering pixels on an infinite screen. Feel the subtle hum of existence, the rhythmic flow of time, and wonder if these are not the echoes of a primordial explosion, but the silent, ceaseless thrum of a cosmic supercomputer, rendering our reality frame by intricate frame. The Big Bang might have been the ultimate on-switch, but the grand program of our universe continues to run, and we, its conscious inhabitants, are part of its endless, breathtaking code.